Hello, I am Richard Schutzline. Today, I'll be presenting the power plant and propeller system on the Beechcraft King Air BE200, which uses the Pratt Whitney PT6A-42 turboprop engine. I'll explain how the engine is built, how it operates, and how it works together with the propeller system. I'll also cover normal operations, abnormal conditions, cockpit indications, malfunctions, and what other systems can be impacted when something goes wrong. By the end, you'll have a full understanding of what keeps the King Air's engines running smoothly and what pilots must consider if problems occur. The King Air B200 is powered by two PT6A-42 engines, each producing 850 shaft horsepower. This engine uses a free turbine, reverse flow design, which means the gas generator spool and power turbine spool are not mechanically linked. That improves starting, response time, and reliability. Air enters the rear of the engine and flows forward, which keeps the engine compact and efficient. This design is one of the reasons the PT6 family has become one of the most reliable turboprop engines in aviation. In this first stage, known as the air intake section, it involves taking air, then sending it to the compressors. The compressor for the King Air is a hybrid design made up of three axial stages and one centrifugal stage. The axial stages handle the initial compression efficiently, and the centrifugal stage gives a strong final boost in pressure before the air enters the combustor. This combination allows for a high pressure ratio in a very small package. After leaving the compressor, the air reverses direction and continues into the combustor. The combustor is a reverse flow, single annular chamber with 14 fuel nozzles and 2 igniters. Fuel from the FCU is sprayed evenly around the chamber, mixes with the compressed air, and burns steadily. The reverse flow design helps maintain stable combustion, reduces engine length, and improves efficiency. After combustion, the hot gases turn forward again and enter the turbine stages. The turbine section includes one gas generator turbine stage and two free power turbine stages. The gas generator turbine drives the compressor and accessory gearbox, while the free power turbines extract energy to spin the propeller through the reduction gearbox. Because the power turbine is independent of the compressor spool, the propeller load does not affect compressor speed directly, making the engine smooth and responsive. The PT6 exhaust system uses two stainless steel exhaust ducts that face upward and outward. Because the engine is reverse flow, the exhaust port sits towards the front of the nacelle. This design keeps the exhaust heat away from the fuselage and reduces staining on the nacelle. The system maintains low back pressure, which helps protect turbine efficiency and engine performance. The reduction gearbox is mounted at the very front of the engine and is the first thing you see on a PT6. It takes the extremely high RPM of the free power turbine, which is spinning at tens of thousands of RPMs, and reduces it to the propeller's operating speed of about 2,000 RPMs. Inside the gearbox are planetary gears, bearings, and torque measuring components. This gearbox also houses the propeller shaft and drives the propeller governor. Chip detectors monitor for metal contamination to protect the pilot from gearbox failure. The accessory drive is located at the aft end of the engine and is powered by the compressor turbine. The drive powers the high pressure fuel pump, the fuel control unit, the lubrication pump, and scavenge pumps, the N1 tach generator, the start generator, the low pressure fuel boost pump, and on the right engine only, the refrigerant compressor for the air conditioning system. Without this accessory gearbox, the engine could not regulate fuel, generate electricity, or circulate oil. The PT6A-42 uses a dry sump lubrication system. Oil is stored in a separate tank pressurized by the oil pump and sent to the bearings, gearbox, and turbine components. Several scavenge pumps return the oil to the tank, ensuring proper circulation in all flight attitudes. Filters, chip detectors, and an oil cooler help maintain oil quality and temperature. Reliable lubrication is essential for the engine's long life and safety. The engine uses a dual-channel fuel system that begins with a low-pressure boost pump, followed by an engine-driven high-pressure pump. The Fuel Control Unit, or FCU, meters fuel based on pilot input, compressor speed, and temperature. Fuel is then sent to 14 fuel nozzles for combustion. Filters and bypass valves protect the engine from contamination and allow continued operation even if a filter becomes blocked. On to the King Air's propeller. The King Air BE200 uses a 4-blade, constant speed, full feathering, reversible propeller system. The prop governor automatically maintains the second RPMs by adjusting the blade angle. If an engine fails, the propeller can be feathered, reducing drag and improving single engine performance. Reverse thrust is available during landing and dramatically improves braking and maneuvering on the ground. Inside each prop hub is a pitch change mechanism that uses oil pressure to move a piston. Oil pressure drives the blades to low pitch, while springs and counterweights move the blades toward the feather when pressure is lost. Propeller RPMs is normally set at 2000. A prop sync or synchrophaser system helps minimize noise and vibration. Electrically heated de-ice boots prevent ice buildup in icing conditions. In normal operating conditions, they focus on maintaining torque, turbine temp, N1, and prop RPM with their published ranges. The engine typically operates around 850 shaft horsepower during takeoff with a 2000 RPM prop speed. Oil pressure, oil temperature, and fuel flow must remain in their normal ranges. The propeller stays between 1800 and 2000 RPMs in flight. An auto feather should be armed for takeoff and climb. The system has several alternate modes, such as manual and automatic feathering, reverse thrust for ground operations, and oil and fuel bypass modes that protect the engine if filters are blocked. These modes ensure that the engine and propeller can continue functioning safely even under abnormal or degraded conditions. In the cockpit, the pilot monitors torque, turbine temp, oil temperature, oil pressure, and fuel. Annunciators warn of chip detection, low oil pressure, or high temperature. For the propeller, the pilot watches RPM, auto feather lights, and prop sync indicators. These instruments are vital for recognizing problems early and preventing further damage. Common engine malfunctions include overtemp conditions, compressor stalls, FCU malfunctions, low oil pressure, and metal detected in the gearbox. Propeller malfunctions may include overspeed, failure to feather, uncommanded feathering, or loss of oil pressure that drives the blades to feather. Each malfunction creates recognizable symptoms such as surging, rising temperature, torque loss, vibration, or RPM instability. Engine or propeller failures can affect many other systems. Electrical power may be reduced if the starter generator fails. Bleed air loss can impact pressurization, cabin heating, and de-icing boots. On the right wing, a failure can disable the air conditioning compressor. Fuel crossfeed may be required when one engine is secured. These interactions make power plant failures especially significant in multi-engine aircraft. When a malfunction does occur, the pilot must maintain directional control, especially with asymmetric thrust. The next step is to confirm the failing engine using torque and turbine temperature. The pilot then performs memory items such as feathering the prop and following checklists. Single engine performance, terrain, and weather must be considered when deciding whether to continue or divert to another airport.